Welcome to this talk on robots for fun and research today. You might be wondering what the hell is a robotics talk doing on a hacker conference? So I moved from hacking to research a long time ago already, and I'm using robots also as tools to find out about human intelligence, about intelligent behavior by humans and animals, and I think that's a nice connection to chaos and hacking. So this talk will be about some recent development in robotics. I'm not going to talk about industrial robotics. It's more about robots for scientific research fields like biology or psychology. And, well, please ask any questions if anything is unclear during the talk, but there will also be a question session at the end. So to make a short outline, oh, by the way, here are some Sony Aibos, but this is not a promotion for Sony. And actually, if you want to hear something interesting about the naughty things that Sony did this year, just in an hour there's a talk by Fukami in room 4 about the Sony rootkit. So I'm going to start with giving a short overview on the history of robotics. Then I'll show you I picked out some specific research issues in robotics. We will see the social issues of robotics, what is robot hardware hacking, and of course, can't be missing here, some security issues with modern robots, and we're going to ask what's going to happen in the future. So starting with a short history of robots in artificial intelligence. Some people say it's starting much earlier with Da Vinci, who already built intelligent machines. But let's start in the 18th century. There were some early animated machines, for example, the automated duck by Vaucanson. He was a monk in France, and he built this duck, this machine, who could even drink, eat, and shit. And the chief of the monastery didn't like it so much, so he was thrown out of it, but he continued building robots. And then a few years later, actually only the term we have today, robot, was coined by Karel Čapek, a Czech guy. And robot came originally from the word for worker or hard labor in Czech, meaning robota. And if you know the German word for work, which is Arbeit, and you remove the vowels, you can still see it's very similar to robot, Arbeit and robot. And of course, everybody, or most of you know Asimov's laws of robotics. If you've seen they recently showed up in a movie about his novel in I, Robot. So meaning that a robot shouldn't injure a human being and so on and so forth. You know that. Then in the 1940s, 50s, you see here on the left an example of early, quite advanced robotics. These are Gray Walters turtles in English, and they're called Elsie and Elmer, and they've been built completely in analog hardware, but had already some complicated interaction behavior. People interpreted their behavior even as emotional. The two robots were moving around each other, and they said, oh, these robots are in love, these robots are performing a dance, and things like that. And that was already in the 1940s. And from that on, everything was going downhill again. So only in '69, we had the first autonomous robot of our time, which was Shaky from Stanford, California. This robot could autonomously navigate around obstacles with about, I think, 1 meter per 7 minutes or so. So it was just incredibly slow. Then later in the 1980s, we were going back to really behavior-based robots, which Gray Walter did already in the late 40s. This was a discipline founded by Rodney Brooks from MIT. And so we were also looking really at reactive robots. So a robot was only reacting at the environment and didn't have internally any representation or any brain. This changed the last, let's say, 20 years a bit when the event of entertainment robots started, because then with entertainment robots, people wanted to have something interesting. They wanted to have robots who really did something, who really showed intelligence, and then there was no point in doing either the very easy, just reactive thing, or just putting a very complicated brain and old AI stuff into a robot. And then people were thinking that, giving this example here, about the importance of embodiment. So they were saying it's not really possible to have intelligence without having a body. And it's all about having senses and actuators and having perception of the world. And a big philosophical discussion came up when Deep Blue was beating the world champion in chess, Kasparov, in, I think it was 1998. And before, people were saying, oh, intelligent machines, intelligent robot doesn't really exist. But then this event happened, and people said, so what? It beat the guy in chess, but it doesn't really change anything. So maybe true intelligence in robots can be more seen in robots playing football, for example. So it's much more complicated than beating a human being in chess, than beating a human football team. This continued. We can skip that slide. How can we use robots as research tools? And why do we want to use robots as research tools? So there's several examples or several good reasons for doing that. First, the robots have reproducible behavior in comparison to animals, to doing experiment on animals to find out about animal behavior, animal intelligence. Second, the internal states, they can be accessed very easily. And the third point, the robots survive most of the experiments. Most. So if we want to combine the field robotics and biology, that's called biorobotics. And we call that understanding by building. And these are the methods that are used. Well, this is a roboticist who wants to build a robot who does the behavior of an ant. So by first building a model of the natural agent, which could be either a simulation or a real robot, then we can abstract general principles of intelligence and apply these general principles to the design of intelligent devices. And then we look at the intelligent device and go into a loop and repeat the whole thing until we're satisfied with our machine. So staying with the example of a roboticist wanting to build a desert ant, I just show some short example of a project we had together with some biologists in Zurich. They were studying the desert ant Cataclyphus for over 20 years, and this desert ant has one speciality. It lives in the Tunisian desert and doesn't lay pheromone trails as the European and German and Berlin ants do. So normal ants, they leave these pheromone trails and then they can easily navigate around these trails. But in the Tunisian desert, the pheromones do evaporate very quickly. So these ants had to evolve to use different strategies than that one. And they can navigate for about 200 meters and then find back to their nest, which is just this small little hole in the desert ground. So they have to navigate really exactly. And the biologists, they had several theories or assumptions how this tiny little ant can do that. And we thought, well, we're going to test this with some robots. So we went also into the Tunisian desert with this robot here called Zahabot and tested some of these navigation strategies or hypotheses the biologists came up. This one is called a snapshot model. So they said the ant is taking a omnidirectional snapshot at a nest, storing that, then going away from the nest, and again taking a snapshot, and comparing these two snapshots to find a vector which is pointing back to the nest. So that was the theory of the biologists. And we built this model into a robot and tested it under the same conditions. I can show a quick movie here of Sahabot in the Tunisian desert. So that was the field. It was very flat and hardly any landmarks, just these cylinders. The robot was driven manually out of the field, away from the nest. It already took a snapshot in the middle of the nest of the field. And roughly around that point, the robot is put into autonomous mode and is told to apply the snapshot model to navigate back to the nest. So now the robot is navigating autonomously. And in fact, the robot is driving back to the position where it started. So we kind of confirmed that the model is sort of working. And there was another hypothesis about these navigation strategies called the ALV model. And a colleague of mine, Ralf Möller, also from the iLab, who is now at Bielefeld, built this robot completely with analog hardware. So that's also quite interesting because here you don't have the separation between the body and the brain anymore. And this robot was built to use the ALV model to navigate back to the home position, exactly the same method than the arms were supposedly doing that. So we can see here in the video, the robot is put in this area, it's taking a snapshot, then it's replaced, and very quickly driving back to the original position. So that movie is double speed, by the way. So now the interesting thing came. The two examples before, we hard-coded the models into the robots. So now we were interested whether the robot was also able to learn one of these models, or maybe a different model. And we designed different neural networks. If you've been in the talk yesterday about machine learning, maybe that's kind of similar. So the robot was put into a room and was just exploring the room for 5 minutes, always taking snapshots and always feeding these snapshots into the neural network. Always 2 connected snapshots. And as the desired result, we had the direction of the line connecting the 2 positions where these snapshots have been taken. And after this exploration tour of around 5 minutes, the weights of the neural network, they converged, they've been learned, and we could use that neural network as a way of having the robot navigate autonomously and having learned this navigation strategy. And in fact, it worked. So the robot only took 5 minutes to learn a general model of navigation in any environment. In fact, we could learn it in one room, take the robot in a different room, and it could apply the learned model there. So it was completely generalized. So one of the results is that the visual homing was possible. You see here the angle error of the homing vector. The angle error is just the angle between the real direction and the direction the robot was taking. And you see it's still quite high, but it goes, after a few minutes, it goes below 90 degrees. And as you can imagine, if you have an error which is always